One of them is how do you invert these equations? Invert meaning, what does this equation do? Given x, y, z, t, measurement done by Alice, let's say, or more formally we call that observer who is measuring x, y, z, t, rather unimaginatively as the unprimed observer, the one for whom the symbols would have primes. The dash is actually a prime. That's what the formal name of the symbol is. And so we are trying to convert measurements by the unprimed observer to measurements by the other observer who is called a primed observer. We have been calling them Alice and Bob. Okay? The inverse of this would of course involve given x prime, y prime, z prime and t prime, that is measurements done by the primed observer, in our case Bob, how do you find out Alice's measurements? Now, of course, one way to do that is very simple. These are all ultimately simple equations. Despite the fact that they have other complicated looking cofactors, these are just linear equations, right? X into something plus t into something is equal to x prime. Here also t into something plus x into something is equal to t prime. So these are just linear equations which you can easily solve. And by solving them, I would be able to find x, t, y and z in terms of x prime, t prime, y prime, z prime. Of course, the easiest ones to do would be this. These are easy, these are almost trivial. The non-trivial part is solving for x and t in terms of x prime and t prime, which is also pretty easy to do. Ultimately, it's a 2 by 2 situation, right? 2 equations in 2 variables. How difficult can it be? It's really not very difficult. But there is a way to solve this without solving this at all. Just relying on the basic postulate of relativity. After all, what does this tell you? This tells you, given an observer, Alice, how do you find out the measurements of another observer, Bob? What we are asking now is, given measurements by Bob, how do you find measurements by Alice? Laws of physics should be the same for everybody. That doesn't mean that the transformation will be exactly the same, because the parameter v is going into the transformation. What is v? V is the velocity actually, it's not really the speed. It is the speed, but the sign matters. In one dimension, of course, you have only v and minus v. Bob's velocity with respect to Alice is plus v, v in the right towards right. Alice's velocity with respect to Bob would be minus v. So, postulate of relativity should inspire you to think this way. That this should work. Just change the v to minus v everywhere. Of course, v square doesn't change, but these do change sign. And once you do that, you are done. Okay? You should check that this is actually exactly what you get when you solve the first set of equations to get x and y and z and t. Okay? But the important point is, whenever a Lorentz transformation is given, even a more complicated Lorentz transformation, the inverse can simply be found out by inverting or reversing the velocity, right? The velocity between the two observers. Yeah. In this case, v is the velocity of Bob measured by Alice in the original thing. So that was plus v. And in the inverse, what you should put in is the velocity of Alice measured by Bob. Velocity of one observer. So you start with an observer whose measurements you have. We are calling that the unprimed observer, just to sort of keep names out of it. Okay? So x, y, z, t is what she measures. Okay? She also measures the velocity of the other observer. Right? So everything, x, y, z, t and v are measurements done by Alice. So if you use that, you get x prime is x minus vt by square root of 1 minus v square by c square. Now when you are actually going to figure out the other way round, things other way round, you are really now asking, I have measurements by Bob, which I am calling x prime, y prime, z prime, t prime. How do I find out measurements done by Alice, X, Y, Z, T? The fact that Bob's measurements are called X prime, Y prime, Z prime, T prime, and Alice's are called X, Y, Z, T is just an accident. Whoever is measuring first, that person's whoever's measurement I'm considering as the input, you have to also use that person's measurement of the other person's velocity. So when you're talking of this, the inverse Lorentz transformation, of course the inverse special Lorentz transformation, what you are saying is, okay, Bob has measured X prime, Y prime, Z prime, T prime. I want Alice's measurements. So for that I need Alice's velocity with respect to Bob. And I can just plug in Alice's velocity with respect to Bob in the original formula and I'm done. I don't need to change anything else. Okay. The only thing it changes is the V that is there in this equation, the original equation. What's the velocity of Bob with respect to Alice? Right? And the V that has to be in this equation, which has to be put in here, the velocity which has to be put in here, to get the inverse, is Alice's velocity with respect to Bob. And since Alice's velocity with respect to Bob is minus V, all you do is plug in minus V in this equation instead of V everywhere, and you get the inverse transformation. What you should of course check is that if you solve the first two equations, if you solve all four equations, you actually get the other four equations. I am focusing on the first two because only the first two need solving. Y prime equal to Y, obviously tells you Y equals Y prime. Right? So these two equations are trivial to solve, the lower two. The upper two are also pretty easy to solve. They are 2 by 2 equations. Pretty easy algebra to solve this and see that this is what you are going to get. Okay. The next thing I am going to talk about is actually a bit of window dressing. It's sort of making the equation look a bit better or nicer. But it actually turns out to be very useful. It's not just plain cosmetics. So here we have 4 coordinates. Remember, all 4 are coordinates now. All 4 describe an event. And the important thing is all of the 4 have to be taken together. Because if you want to talk about measurements done by some other observer, you need to know all the 4 as measured by the previous observer to figure out the new ones. Knowing only X will not tell you X prime. Knowing only T will not tell you T prime. In this special situation, it might seem like knowing only Y will tell you Y prime, which is correct actually. But that happens only because we are talking about a very special kind of Lorentz transformation. If your relative velocity had been along the y-axis, for example, that would be easy to write. Same kind of equation, so instead of x being changed, y will have y prime minus dt by square root of 1 minus v square x, and so on. And of course, the general velocity could be in a very complicated direction. It doesn't have to be along one of the axes. So in general, all 4 coordinates would mix up with each other, and to know x prime, y prime, z prime, t prime, you will have to know all of x, y, z, t. Okay. In other words, knowing x, y, z, t completely specifies an event, which ensures that once you know the event completely, you should be able to figure out its coordinates as measured by somebody else. And that is exactly what the transformation rule does. Yeah.
So are you saying that all the velocities should be simultaneous?
Well, there is no, you are only measuring an event, single event, right? There is no notion of simultaneity involved because simultaneity involves 2 events. An event is labeled by veritocus and veritocus. Veritocus is x, y, z, veritocus is t. So simultaneity does not come into the picture here at all. When you talk of simultaneity, you talk of 2 different events, whether they are simultaneous or not. To pinpoint or label an event precisely, you need to know where and when, x, y, z and t. Okay. So simultaneity, you might say, even is trivial. There is no notion of simultaneity simply because you are talking about only one. 2 different events whenever you talk about it, like measuring something here and something there, of course their simultaneity plays a huge role. Might play a huge role depending on what kind of measurement you are doing. Here, for a single event, it doesn't really make sense to talk about them as simultaneous. Of course, you might always say that these are not single events, these are always intervals between x, y, z, t and 0, 0, 0, 0. But that of course is not simultaneous with this, right? 0, 0, 0, 0 occurs at t equal to 0. This event occurs at t equal to t. Different values. Not simultaneous. So even there simultaneity is not involved. You need to know all four at the same time, although that at the same time is not the same. It's just the English language at the same time. Not at the same time as far as physics measurements are concerned. Maybe that's what you meant when you said simultaneous. You need to know all four to pinpoint an event. Okay? Now, so you have four coordinates. And I'm pretty sure you have seen this also done in 3 dimensions. Instead of talking about x, y, z, you often say x1, x2, x3. Why do you do that? Why x1, x2, x3? Sorry, could you be louder? No, I'm saying in 3 dimensions. Here we are no longer talking in 1 dimension, we are talking in 4. 3 plus 1. Okay. We have left the 1 plus 1 world a while ago. You have 4 coordinates on the board right now. But I'm saying in 3D, ordinary vectors, instead of saying x component, y component, z component, you often write things like x1, x2, x3. Or vector component, you write a1, a2, a3. Have you seen that before? Why do you do that?
So because, intuitively speaking, z has always been up, x and y have all been a plane, but an observer in space like Einstein's thought experiments wouldn't know
good point. That there is no reason why x should be very special, y should be very special. That's what you're saying. Yeah, but I had something more prosaic in mind. Something more, just about something neater for calculations. Like, have you seen this done? EI, that's E1, E2, E3 are the key unit vectors, right? You dot EI with EJ. What do you get? No. You get delta IJ. Now this is how many equations is this? So how many? I into j equations. I is if I is 0, 1, I is 1, j is 1, then it's only 1. I can take how many values? Not. Yeah, right now we are talking about 3D. Let's just see. 9 values. These are actually 9 equations, which you roll up in 1. When stuck to the old notation, you would have write I dot I equals 1, I dot j equals 0, I dot k equals 1 equals 0, and all 9 of them. Of course, you might say that okay, dot products are symmetric, so I don't really need to write all 9. Maybe 6 will do, but still quite a lot. Rolling them up into a single equation is possible because you are using numerical labels to talk about the different things. So it's just that convenience. So you write a vector v. As you have seen this before? Without the sigma or with the sigma? This is sigma I equals 1 to 3, right? Now a particular person who hated very complicated mathematics figured out that his equations were getting too complicated because of lots of sigmas that he had to write. So he came up with this convention that at least in whatever he was doing, if an index is repeated, unless otherwise mentioned, it would imply that the sum is being done. That is, if you just write vi, ei and did not write the sigma, even then you would understand the sum is being done. Okay? So, you would just write this. That and it would work somewhat like this. Of course, he did not really use it for ordinary 3D algebra, although you could. In fact, you can. Have you used this before? Right? What is this called? That is called the Kronecker delta. What is this convention called? The sum is that you can drop the sum. It's the Einstein summation convention. Einstein cooked it up when he was doing general theory of relativity, where he had to do a lot of sums. writing all those sums became very, very nasty. So it made his work look horrible. To drop all the sigma signs from there, it looked a lot neater and it was also pretty powerful to do calculations. Okay? So he essentially came up with this convention. If you repeat an index, you can assume the sum being done at the back of your mind. You don't have to worry about this. And the advantage is, so sorry, you should have W vector here. You could do something like this. V dot W is VI EI dotted with WJ EJ. And here I have done something which, again, you must have realized. The idea is, I could have written this as VI EI, this also as WI EI. But when you put them together, you have a problem. AI BI means A1 B1 plus A2 B2 plus A3 B3. EI DI means C1 D1 plus C2 D2 plus C3 D3. But AI BI times CI DI in this convention does not mean the product of AI BI times CI DI. Why? Because if you were to multiply AI BI by CI DI, you should get terms also like A1 D1 C2 D2. Right? A1 D1 plus A2 D2 plus A3 D3. Multiplied by C1 D1 plus C2 D2 plus C3 D3. You would actually get terms like A1 B1 C1 D1, of course you will get. But you will also get terms like A1 B1 C2 D2. Okay? So if you wrote this as AI BI CJ DJ, where the sum over I and j were both implied, then it's perfectly okay. But if you wrote it as AI BI CI DI, you would be dropping many terms. Right? So the important point is, these indices where you are doing a sum, they are called dummy indices of summation. Dummy indices simply because you can't give them a value. You can't say what is the value of this for I equal to 1, right? Or I equal to 2. This is never for a particular I. This always means V1 E1 plus V2 E2 plus V3, right? So giving a value of I here doesn't make sense. I has taken all the possible values and you are summing it up. Okay, so you can't ask what is the value of VI EI when I is 1. That makes no sense whatsoever. Okay, that's true for all dummy indices. And whether you call a dummy index I or J or K or L or M or whatever, any letter you want to think about, makes no difference, right? Instead of calling it VI EI, we called it VAG EA. Repeated index still means V1 E1 plus V2 E2 plus V3 V3. Right? The dummy indices in an expression can be changed to anything else you want. The only point is when you are coupling them together, especially when you are multiplying them, you have to make sure that you don't accidentally end up making two different expressions have the same dummy index. Because then you will be losing terms like A1, B1, C2, D2. But here, in this particular example, that will not make a sure difference. But the calculation that you would do would go like this. EI dot EJ. And EI dot EJ is delta IJ, something you have already figured out. Or something you already know. And so you get VI WJ delta IJ. Right? And what is VI WJ delta IJ? It's a sum over both I and J. Now, which one do you sum up first? Over I or over J? Doesn't matter. People preferably sum up over J simply because of bias. That's just a cultural bias, that you sum up over the second one in the alphabet than the first one. Because you are meant to sum up over both I and J, you can do it in any order you want. But if you sum up over J first, then J takes all possible values. But delta Ij vanishes unless J is equal to I. Okay? Yeah. So this notation simply. Okay, so yeah, I'm just saying that this is basic. So you have understood what this is? Oh. Wait. You have seen this, right? Okay, I was assuming that people have already seen this in some class before. Okay, you have seen this, right? Vxi plus Vyj plus Vxk. Okay, when I ask have you seen this, I usually mean have you seen this in a class. If you have seen this outside, please say that. Okay, but otherwise, somebody speaks up and says, I have seen this, I assume the whole class has seen this because the assumption is this was in a class. This used to be taught in the mechanics class before, when it used to be a full three credit course, but now it's of course 2 credits, so things are reduced. This one may not have been covered. Everybody knows that one, right?
Yeah.
So when I said numerical values, all I meant for the indices, instead of x, y, z as indices or I, j, k as the unit vectors, we use v1, v2, v3, where v1 simply means vx, v2 means vy, v3 means vz. Okay? And instead of I, j, k, we say e1, e2, e3, 3 unit vectors. By the way, why is unit vectors called e? Any idea? Okay, let's see how many linguists we have in this class. Why are unit vectors called e?
Because they can be made as eigenvectors and you can just take the basis out and...
You are in the right direction because the name eigenvector comes from the same language.
True, German.
Ein in German. One in ein. German mathematicians did most of the work in this. So basically, the German language has lots of inputs here. E1, E2, E3 is just ein 1, ein 2, ein 3. Of course, that's a combination of both German and English. But E is essentially used because when people first wrote this down, Germans wrote this down, so they obviously used their unit, which was ein. So in that language, this becomes V1, E1, nothing but Vxi plus V2, E2 plus V3, E3. Okay? So you can of course write this. Now that you have this numerical indices, you have the advantage that you can write this as a sum, right? I going from 1 to 3. Okay? Everybody knows the sigma notation, right? And then what Einstein said is too many sigmas are ruining the appearance of everything he writes. So let's not write the sigma. That's it. And everybody caught on because it turns out to be a very, very powerful thing to do. Too many sigmas actually spoil the broth very badly. So, okay. So, in the next step, all we are saying is this: once you have dropped the sigma notation, you have to understand this I is being summed over. But whether you write the sigma or not, the index that is being summed over has no specific value. Right? You can't say what is Vi Ei for I equals 1. Because Vi Ei always means V1 E1 plus V2 E2 plus V3 E3. All 3 terms added together. Okay. Could be all n terms added together if you are in an n-dimensional world. But right now we are in a 3-dimensional world. So later on we will be in a 4-dimensional world. That's our class really. So there you will see more values which n can take. But all values that I can take, it will take all those values. Okay. Now, when you do a calculation like V dot W, V vector dotted with W vector. V vector can be written down as Vi Ei. It's just simply Vx I hat plus Vy j hat plus Vz k hat in disguise, right? W vector can be written down as Wj Ej. Repeated index, same sum being implied. The only thing you have to be careful about is because we have, as long as V and W were 2 separate entities, we could be perfectly happy saying V is Vi Ei and W is Wi Ei. Using the same index in both cases makes no difference, right? But when you multiply them together, in this case do a dot product, you have to be very careful that you do not mix up this index with this index. When we are going to do a sum over this and a sum over this, right? Just with numbers, if AI BI means A1 B1 plus A2 B2 plus A3 B3, and CI DI means C1 D1 plus C2 D2 plus C3 D3 separately, trying to multiply them together by writing this would be a disaster. Because this will only have 3 terms, A1 B1 C1 D1 plus A2 B2 C2 D2 plus A3 B3 C3 D3. all cross terms will be dropped. But that's wrong. In this case, of course, for the dot product, that doesn't matter because of the cross terms being 0, right? E1.E2 is 0, E1.E3 is 0. It doesn't matter if you drop the cross terms in this particular calculation. But in almost every calculation, cross terms will matter. So you have to realize that CI, instead of calling this CI/BI, could have easily called this CJ/DJ, right? It would have meant exactly the same thing. And then when you multiply, we just know this is AI, BI, CJ, DJ, no problem would arise. Because then it would be sum up over I going from 1 to 3, all possible values, J going from 1 to 3, all possible values. And then you will get A1, B1, C1, D1, you will also get A1, B1, C2, D2 and all that. Okay? Yeah? So that's what this notation really means. Now today, in fact, we don't even need to go into the details of this notation and calculation with this. But let me just finish this. You have VI, WJ, EI.EJ. Now this looks trivial, but there is a huge amount of mathematics which is hidden in this. What are you really doing? You are doing VI, EI, that's the sum of a bunch of vectors, right? VI, EI itself is the sum of 3 vectors, E1, E2, E3, multiplied by V1, V2, V3. You are multiplying that by WJ, EJ. Another sum of 3 different vectors multiplied by 3 different numbers. And here what have you done? You have just put the VI, WJ out. You are actually using a very important property of the dot product here, something called the distributive property. It is being done without even thinking. It's like you are just moving the WJ in front. You are actually, if you wrote it out in full, you would realize that you are actually using the fact that you have a bracket here in V1, V1 plus V2, V2 plus V3, V3, another bracket here. You are taking each term in the bracket and multiplying it with each other term, which you can do because the dot product distributes. A into B plus C is AB plus AC. The same property as ordinary multiplication has. And then EI.EJ is delta IJ. You are still supposed to sum this, right? VI, WI, delta IJ. Sum over both I and J. I will take 3 values, J will take 3 values. You have to sum up all 9 terms. So still 9 terms, right? But when you sum up over J, delta IJ will always be 0. Unless J is the same as I, right? Which means, in all out of all the terms, the only terms that will survive are the ones in which J is the same as I. And when J is the same as I, delta Ij is simply 1. So, using the delta, this becomes very, very easy to do. This becomes VI, WI, still sum over I, right? And this means V1, W1 plus V2, W2 plus V3, W3. The formula for dot product that you all know. Okay. Now, this is a very trivial example. And if this was the only thing you could use this notation for, it would hardly be worth studying it. Yeah. We are not there yet. Right now, we are in a 3-dimensional world. In a 3-dimensional world, there is no such thing as upstairs index or downstairs index. That depends because, okay, we'll talk about that. In the 3D world, there's a specific transformation that we talk about, not that kind of transformation that we are talking. If you wanted to talk about that transformation, then you are talking. But that was an aside. Let's not worry about that right now, because we will talk about all these upstairs, downstairs index business soon. Even I will do it right now, although I will not explain why. But here, let's come back here. How many coordinates do we have? 4. X, Y, Z and T. So how do you label them? X1, X2, X3 is sort of easy. X, Y, Z is still X1, X2, X3. The issue is with T.
CT.
Well, first of all, it has to be CT because T has the wrong dimension. So better have everything with the same dimension. So we will use CT. Now we have 2 choices. One, the first one that was used basically because of this thing that we had seen before. this quantity or its negative, both are invariant, right? This is an invariant quantity. What that means is no matter which observer measures it, two different observers will measure two different values of two different sets of values for t, x, y, z, but they will all agree about this quantity, right? This is a so-called invariant interval that we were talking about. Okay? Now this looks very much like another invariant that we all know from rotation of coordinates. When you rotate your coordinate system, x, y, z changes to x prime, y prime, z prime. In general, all of the coordinates change. The one thing which doesn't change is x square plus y square plus z square. Of course, we usually talk about the square root, which is the length, but square root that not changing is the original thing, of course, doesn't change. So x square plus y square plus z square is an invariant under rotation. This is an invariant under Lorentz transformations. So one important thing is when you say something is invariant or something transforms in a particular manner, all of these only make sense provided you specify which transformation you are talking about. X square plus y square plus z square is an invariant for rotations. It's not an invariant for Lorentz transformations. T is actually an invariant for rotations. If you rotate your coordinate system, nobody even bothers to telling you that t is equal to t prime, right? Rotating the coordinate system, t doesn't change, only x, y, z does. So t is an invariant when you're talking about rotations, but it's not an invariant when you're talking about Lorentz transformations. But for Lorentz transformations, this whole thing is an invariant, and because you want it to sort of mimic what you already know, people are actually very shy or reluctant to pick up new things. Everybody knows this is an invariant for rotations. That is very similar, but with a minus sign. And the minus sign makes all the difference, really. But there's a very easy way to get rid of the minus sign. Which is, like this is ICT host. This is what was done historically when this was first introduced by somebody called Hermann Minkowski. Minkowski was actually a math teacher who taught Einstein math. According to his and Einstein's admission, not very well. At least the outcome was not very good, according to both of them. But anyway, what Minkowski did was when he found his student actually worked out a new kind of transformation, which of course, by the way, Lorentz transformation had been around even before Einstein. That's why it's called Lorentz transformation. Lorentz did this as a mathematical exercise as a transformation which would keep Maxwell's equations covariant. But that was done only as a mathematical exercise. There was no real reason to believe that that would be the transformation law between two inertial observers. Einstein first gave it physical meaning, and now Lorentz said, okay, fine, it can be thought of as a rotation just like our ordinary well-known rotation, things we already know. All you have to do is imagine that the fourth coordinate, you are in 4 dimensions, number one, and the fourth coordinate is imaginary. Okay. So, in old books, and preferably only in old books, you will see notation like x0 is x, x1 is y, x1 is x. I fell in the matter in the computer scientist fallacy of starting with 0. And x4 is ICT. Okay, I'm saying old books, but many of the books still in use. Yeah.
So why was there a minus c square p square n? Like why was the minus c?
Because it's there. Okay, that's a glib answer. Because it's there because we had worked it out, right? Remember? We had shown that T1, T2 is x square by c square minus t square, and that's the same for both observers. Okay? That was for 1 plus 1, in 3 plus 1 is there. But there's another deeper reason for that. Minus c square t square plus x square plus y square plus z square equals 0. What does that describe? So if a light signal starts at the origin, any point, any event on the path of that light signal as it spreads out. Do you agree with this? Right? X square plus y square plus z square equals c square t square. We're simply saying that it travels with the speed of light. Light travels with the speed of light. What else? But the important point is this thing has to be true for all observers. That is x square plus y square plus z square minus c square t square equals 0. For any event would mean some other observer would also see x prime square plus y prime square plus z prime square minus c square t square, same c, t prime square equals 0. Why? Simply the statement that both observers agree as to where their origin is. Remember we have said that they both start their clocks when they cross each other. So x, y, z, zt equals 0 is the same for both. And x prime square plus y prime square plus z prime square minus c square t prime square equals 0 is simply the statement that the speed of light for this other observers also see the same in all directions. Right? Yeah.
So if my compared to a certain frame of reference x, y, z, if my delta x, delta y, delta z is 0, that means that I am
delta x, delta y, delta z is 0 or delta t is also 0?
So I will be traveling at the speed of light in the time axis. Should be.
What does it mean?
If my x, if I am just sitting here right now.
Yeah, your c delta t changes at the speed at c times delta t.
So I'll be.
That doesn't mean you're traveling anywhere.
But in a time axis, I'll be traveling at the speed of light, right?
You want to say that you multiply c delta t, c delta t by c is traveling at the speed of light? I'm pretty sure nobody else will agree. That doesn't mean traveling, right? Traveling means going from one place to another.
But ICT is also a dimension, right?
True.
So as the time progresses, I am traveling at the speed of light.
But
so why am I not expanding any energy or something like that?
why should you? Because traveling in that's exactly the point. The point is the time axis is not the same as the other axis. You sit still, you're going to travel in time. There's no physics involved there. That's just language. You just stand here. Your x, y, z doesn't change.
But my
Your t changes. T changes anyway. And because you're measuring CT along this axis, it changes 3 times faster than t evolves. That's right. That hardly. So instead of using CT, that's choice of CT is just mathematics, right? You could have chosen t.
So it doesn't actually exist.
It makes no difference whether it doesn't happen anyway. So okay, we will come back to that point in a different manner later. But for the time being, let's just point out this. The reason why Minkowski did this was, if you write it this way, Lorentz transformations are things which keep x1 square plus x2 square plus x3 square plus x4 square invariant. Okay. Now, the only problem that happened with this was people got so pleased with this analogy with rotations, they began to really think of Lorentz transformations as rotations, and then messed up things completely badly because imaginary I is not the same thing as a real number, right? And if you hide the fact that CT is actually a different sign, which is very important. C square T square is a different sign in the invariant as opposed to x, y, and z. The fact that you are hiding this by smuggling in an I actually makes understanding the thing a lot more difficult. Which is why almost no modern book, except for a few people who are very, very old-fashioned, who wrote those books, no modern book uses this. It's a bit of history more than anything else. Modern books use a different kind of notation. For them, it's still x1 equals x, x2 equals y, x3 equals z. But this is now things become a bit weird. We don't write them as a suffix. These are not powers. We are not saying x to the power 1, x to the 2, x to the 3. We are just saying x1, x2, x3. So we are putting the indices upstairs. Why? You will understand that later when we also contrast this with the downstairs version. There is a reason why we do this, but that reason will be clear later. But one thing is, you can say that this is basically distinguished from this one. And you don't have an x4. The notation you have x0, which is simply CT. Okay? So you drop the I. Just the I hides the fact that time is fundamentally different. And that makes life a lot more difficult to thinking about the thing with eyes all the time makes it a lot more difficult to understand what's going on. So people decided that they would drop the I. And just so that people would not confuse this with whatever happened before, they changed the labeling. Instead of calling CT X4, which would confuse people with whether you meant CT or ICT, they use X0. It's just a way to keep these two things separate. Okay? So in modern special relativity, which modern here means anything after the 1940s, I would say. Although some very well-known relativity texts, which are pretty old texts, but well-known because they are pretty good texts, that's a right relativity this day, do use X1, X2, X3, X4. So you have to be aware that this is in the market. But this is universally the thing that people are supposed to use. X0, X1, X2, X3, CT, X, Y, Z. Now, why upstairs, why not downstairs? We will come to those issues later. There is a very good reason why, but right now it's not the time to talk about it. Now, X prime 0. All I'm going to do is rewrite those Lorentz transformation equations in terms of these X0, X1, X2, X notation. So what is X prime 0? Well, CT prime, right? CT prime is CT, that's X0, minus V by C into X, that's X is of course X1. So you get X0 minus X1, but X1 is multiplied by what?
C square.
V by C. Well, it's easy to see that it has to be V by C and not V by C square or V, because X0, X1 are all dimensionally the same, right? So whatever multiplies there has to give dimensionless quantity, and let's use our notation for that. Of course, that was a full equation. I've forgotten about the 1 by square root of 1 minus v square by c square. So there is now name for that. That multiplies the whole thing, right? Gamma x0 minus gamma beta x1. Okay. What is x prime 1? That's even easier because x prime 1 is just x prime. So that's gamma, the overall factor. Now that I am writing this as x0, x1, x2, x3, t comes first, or x0 comes first, x1 comes after that. So I am writing the x in the formula for x prime as the second slot. The first slot should have x0. So what should come in front of that? Minus beta x0, right? Minus vt is the same as minus v by c into c. So this is the compact modern index version of writing a special Lorentz transformation. And it's actually pretty simple, right? In fact, in this form, it's also easy to see that you can write this as a matrix equation. So what should the size of this matrix here be? 4 by 4, right? It's splitting 4 numbers to 4 other numbers. And in this case, this matrix is actually very simple because we are dealing with a special case I don't know whether you have seen this notation before, but it's even easier to write. In blocks. You're writing the 4x4 matrix as 2x2 blocks. So the 0 2x2 is just 4 zeros. 4 zeros and the I 2x2 is the identity. Of course, you can write the full thing out. It's just too much effort on my part to write all the 16 components. It's easier to write this. Well, actually, blocking matrices in this manner consistently is very, very useful because you can actually do things like this. If you have matrix block like this, you have a large matrix which is ABCD are also matrices. Of course, matrices, they have to have the correct number of rows and columns to fit together properly. But if you have two such blocked matrices, the product, the sum is of course A plus E, B plus F, C plus G, D plus H. The product is also like a matrix product, as if it will be on the top corner you will have block which will have A times E plus B times G. The way you multiply matrices.
Is it multiplied beta gamma? Gamma and what is the other term?
This one, gamma minus beta gamma. Minus beta gamma.
Minus, is it multiplied?
Oh, sorry, that's a problem. I made a mistake. Yeah. Yeah, it's multiplied. This element is gamma. That's minus gamma beta. Right? Because that's multiplied, right? This question is gamma. That second question is minus gamma beta. I've just written the gamma outside. So the 4x4 matrix that you have for the special Lorentz transformation is basically gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. That's just a shorthand way of writing all that. The point I was trying to make is if you have block matrices like this, you can add multiply them like ordinary matrices. So at any given stage you are not dealing with a huge matrix, you are dealing with smaller pieces. It actually makes calculation a lot easier for large matrices. If you are dealing with say 8 by 8 matrices, multiplying them together, if you could have a nice natural way of blocking them like this, it will be, especially with many terms 0, like here, it will be a lot easier to calculate it. Yeah. X prime 0 where? Yeah, x prime 0 is ct prime, right? By definition, x0 is ct. So x prime 0 is just the same thing as measured with the other observer. Plus c times t prime. So I just take the second equation that I wrote down there. T prime equals t minus vx by c square by square root of 1 minus v square by c square. Multiply both sides by c. So ct prime is ct, that's x0. Minus vx by c square into c minus v by c into x, that's x1. That's it. This is just the same equation. By the way, today I have done no physics whatsoever. I started with this. I have inverted this, which, okay, you could say that's physics. Because they are changing the sign of v will invert this. That's Einstein's postulate. The first postulate of Newton. Okay? That was the only physics that we have done so far. Everything else is just algebra. Okay? And small change in the whole thing. X0, this one. Oh, I was trying to illustrate that if you had the point, okay, that's an aside, really. If you have blocked matrices like this, two matrices blocked in the same way, you can actually multiply them as if the matrices themselves are just numbers. And do matrix multiplication. So many calculations can be done more easily. So blocking matrices is not just for notational advantage. It's also. Oh, we have not come before. We will. Okay. Now, so far we have been talking about three-dimensional world coordinates, four-dimensional world. Again coordinates. Coordinates mean two different things. In three-dimensional world, coordinates just means x, y, z. The coordinates will tell you where something is. The four-dimensional world, we are talking of events. And coordinates here means not only where something is, also when something is. So where and when both, which means four coordinates. Okay. Now in three-dimensional world, apart from coordinates, we have got some other objects to deal with. We have scalars, we have vectors, we have tensors and other kinds of objects. We also have things called spinors, etc. etc. We are going to not worry about those. But scalars and vectors definitely, tensors also maybe. Now, let's forget all about STR for the time being. Let's go back to the three-dimensional world, where we talk about x, y, z as coordinates and you rotate coordinates. Now, in that world, is the x component of a vector or a scalar? Scalar. Anybody disagrees? The x component of a vector. Forget everything about what you learned about STR and so on. Just go back to first year or even class 12. The x component of a vector, is it a vector or a scalar? Scalar. Now, if you have done a linear algebra class, have you? Then you are perfectly right. In linear, unfortunately, the same word is used in many different meanings. So, scalar in linear algebra simply means the numbers you multiply vectors by. Right? To have a vector space, you have objects which you call vectors. You also have another field, which again means something very different in mathematics as in physics. So unfortunately, same term again. And the elements of that field, which typically in most cases are real numbers or complex numbers, they are called scalars. Okay. If you were using linear algebra language, then x component of a vector, of course, is a scalar because it's a number which you multiply I hat by. So, that would be correct. But we are not talking of that. In physics, there's an entirely different meaning to the word scalar. And just to ensure that we don't confuse the two names, two scalars for the time being, let me use another name which is equivalent, but which makes it obvious that x component of vector is not a scalar. At least not a scalar in this sense. That other name is an invariant. Okay. An invariant quantity. Is x component of vector invariant? Now you must ask, invariant under what? What am I supposed to do? So that you ask whether something varies or not. Here, everything that we are going to say is about rotations. As long as we stick to 3 dimensions, we are going to talk about rotations. When we go to 4 dimensions, we will talk about Lorentz transformations there. Is the x component of vector an invariant? That is, does it stay the same when you rotate your coordinate system?
So, when you talk about x component, do you mean just the coefficient or the...
Just the coefficient. Not the projection. The 3 in the 3i plus 4j plus 5. That looks like a scalar. It is a scalar in the linear algebra language. In physics, scalar, when you later on go and talk about scalar fields and stuff like that, scalars means invariants, things which do not change. Like say the temperature is a scalar. Why? Because no matter what coordinate system you use, the temperature will not change, right, at this point. You will rotate your coordinate system, will the temperature change? A more direct, more obvious example, or non-trivial example rather, is length. X, Y, Z changes. Length doesn't. Length is in that sense a scalar, or an invariant. So is the x component of vector invariant?
No.
Is it a vector?
No.
No. Well, is it anything?
Something.
Okay, let me ask you this. If I told you that the x component, okay, what is the most obvious vector that you know? Unit vector is not an obvious vector. Velocity. Position. Come on. The first vector that everybody knows about is position vector. Everything else actually comes from that in a very important sense. The x component of position vector is simply the x coordinate, right? If I told you the x coordinate of a point is 5, Will you be able to tell me what the x component will be when I rotate my coordinate system? If I tell you how, suppose, okay, in one situation you will be able to tell me, which is if I rotate about the x-axis. But if I rotate about, say, the z-axis to an angle theta, I've told you exactly what my angle theta is. I've told you exactly what rotation I'm carrying out. I've told you the point had an x coordinate of 5. Tell me the new x coordinate. So the x coordinate by itself actually means nothing. Okay, it does mean something. It means something only in the context of that particular coordinate system. But beyond that coordinate system, it means nothing. Real objects should mean something no matter what coordinate system you use. Coordinates are, after all, artificial things that you are putting in the world. The world exists without your coordinate system, right? So, things which depend strongly on a coordinate system are not really very physical. Physics should transcend that, should go beyond just things which depend specifically on coordinates. So what we will do is try to think about how things change. So is the x component of any other vector a vector or a scalar? The answer is no, it's nothing on itself. By itself, it's just very limited information about the thing, which does not tell you what the vector is. To know the vector, you have to know all three components. And when you rotate the coordinate system, all three components could change. Of course, we are rotating about the z-axis, so z component will not change, but that's because you are only rotating specifically about the z-axis. But you have a way in which things change, right? Now, how does a vector change? Or how do vector components change when you rotate your coordinate system?
Rotational methods.
So cos theta, the matrix, the transformation matrix is cos theta.
Which transformation matrix?
Rotational.
Sin theta minus sin theta.
Well, a vector is described by a bunch of three numbers in 3 dimensions, and these three numbers transform when you rotate your coordinate system exactly like the coordinates do. So whatever was the transformation, whatever was the matrix you put in front of x, y, z, x prime, y prime, z prime is cos theta, sin theta, minus sin theta, cos theta, 0, 0, 0, 0, 1, that matrix that you can write down in front of x, y, z. Whatever transformation matrix you have for the coordinates, the same transformation matrix you will have for the vector components. How do we know that? The answer is that's the definition of a vector. That's how a vector is defined. Not something having magnitude and direction is class 10 at best. After all, the moment you start saying magnitude and direction, then you say, oh no, things like, say, current has direction, but current is not a vector. Then you start to say, okay, things like rotation has both magnitude and direction, but it's not a vector because it doesn't commute, and so on. You have to realize that vectors are really not defined that way. Spaces tend to define vectors, rather badly, but the bad definition is this one. A vector is something which is described by a bunch of n numbers, which are in n-dimensional space, which transform under a rotation of coordinates exactly the same way as the coordinates do. Okay. So a vector is defined to be out of time. Next.